Hello, so we can start this session. My name is Vasilios Zagkas from Sim Forward, engineering company in Athens, Greece. And we've organized this webinar in cooperation with Midas NFX in order to try to throw some attention into Midas NFX for FEM analysis in shipbuilding and ship design projects. Today we present a project we have done, which was part of a paper we presented last month, and we will go through steps that we've taken to do a preliminary hydrodynamic analysis to derive pressures on a hull shape, and then further static and nonlinear analysis that took place on the hull. I will go through the presentation, and at the end of the presentation we will have a short look on the actual Midas NFX platform and its integration with our ship structural modeler BVB CAFE. So through the presentation, we will have a short introduction, a note on the integration platform, how we deal with it, what is the modeling approach, and the description of our workflow, the workflow that we have defined according to our needs, analysis and results, and a conclusion. So just to introduce the idea, so ship design and shipbuilding refers to complex products. Ships are inherently very complex structures included by many systems. So it is evident that different groups and teams need to be there to handle specific tasks. So this makes it necessary for information to be handed down from one group to another, and we have a natural cooperation is needed between teams. And it's very often, especially in the shipbuilding industry and in ship design projects, that results come after an iterative process, and you should very often go back, redefine your product, and move forward to the next step. So we have seen that collaborative design is really gaining popularity and importance nowadays in all these complex products industries. And of course, demand for a streamlined workflow. People tend to ask for a streamlined workflow in order to be able to move from one software to another. So the main domains within the ship design project, starting from conceptual design, and then we've moved to the basic design, which is then documented by the detailed design that it's actually one step before the production. But throughout this process, we also have nowadays the advanced engineering that is taking place, which is something which is related to what we talked today. So mainly simulation processes. The project management, of course, with this also has to do with the CAE workflow nowadays, due to the volume of work and the volume of models used in the industry. And lastly, the documentation that has to be produced throughout the design stages. So why we are looking at it nowadays, the license costs for modeling and analysis software are a very important factor. We are not anymore in the era where people do not pay attention to the licensing costs. It is a very important factor, and it's become evident that the model of dedicated software for specific functions is not anymore the best way forward. We have seen that 3 to 5 licensed softwares, they're used on average during the entire course of a design project. And of course, this should throw our attention to the compatibility between the software, because this will compromise our final workflow and the delivery of the project. Due to that, we can see that several companies, they are resorting to a one-code solution or one integrated platform solutions. They try to reduce the license costs by trying to get integrated packages, and also through that they of course try to simplify the workflow to a great extent. I mean, what drives this demand at the moment is of course the current state of the market, and also the expected effects through using CAE solutions. We can see that the current state of the market is the increased cost, the high quality which is requested, and of course a short product cycle nowadays. And through utilizing CAE, we try to cut down the cost, to improve the quality on the other hand, and also have a very short development period as it's requested. So a few words about the integration platform. The integration platform that we are utilizing here is Midas NFX. So I'm sure most of you have an idea about Midas NFX already. So I'll just go through it quickly. We have Midas NFX is an integrated pre-processing, post-processing and solver platform, utilizing a powerful preprocessor. You will also see at the end of this session where we'll have some hands-on work that the workflow is very intuitive. We have a powerful model cleanup through modeling functions, and also sophisticated post-processing graphics to enable comprehensive reporting at the end of your project. Another advantage is the high performance. At the moment, Midas NFX is one of the quickest automessers in the industry, and supports parallel processing by also supporting high quality element meshing. And at the end, of course, what is let's say also very important is the multidisciplinary analysis solutions and the solvers offered within the package. So there is a wide variety of solvers, starting from linear static analysis and going up to let's say complex CFD flow analysis, even for dedicated problems like free surface for marine applications. So if you've also seen the latest Midas NFX webinar release of 2015, you will see many new features that have been included, and something which is not new but it's still very up to date is the topology optimization, which is optimization analysis linked to the static and dynamic solvers. So the whole philosophy between the integration platform is trying to cut down the time and the cost, starting from the design and going to the actual production of a product. So here you can see the traditional versus the design using CAE technology, and you can see that the whole philosophy lies on the quick performance evaluation, starting from the design on the same platform, and then going through the CAE process and having an improved product within the design stage before going to the production planning and thus reducing the time and costs by almost 60 to 70%. Now we can start with the case study. We had our marine case study and the modeling approach. So we started with the with a tugboat. This is a 70-ton bollard pull tugboat coming from a client project, and what we have tried to do here is that assess the hydrodynamic loading of the on the hull, and especially on the aft part of the tugboat, where we have the so-called azimuth thrusters for the propulsion, and where the structure is quite complex and the thrusters are hanging from the structure. Lastly, you will see in this presentation that we have also run a collision analysis between the aft part of the tug to an offshore column installation, in order to assess the impact and also to assess the possible deformation on the shafting that exists on this aft part for the propulsion. So starting, we had to, of course, we have to import our model. We have used a given hull geometry. So Midas has the ability to import a variety of geometrical formats. One of them, and most used at the moment, is the IGS one, and we have used it to import it into Midas NFX. In that case, we will start with the setting up for the hydrodynamic analysis, and to do that, one would have to actually convert. We have to import his model. Model coming into an IGS will probably consist of different faces and surfaces, and or possibly also lines. So one will have to convert his geometry into a BREP solid in order to be able to perform a Boolean operation that we will see below. So we have found that Midas NFX could effectively handle this problem, this geometrical problem, by specific functions, allowing us to stitch the surfaces together, and at the end bind them into a BREP solid. So as I said before, having a big BREP solid now allows us into creating our fluid domain very easily by just utilizing the Boolean operation within Midas NFX. So we have started with creating our fluid domain, which is, let's say, a critical process for starting of the hydrodynamic analysis in this part. We have used the modeling tab of Midas NFX, and we have created a solid box where we have given the appropriate dimensions according to our hydrodynamic needs. So we have a size, we have an air domain, and we have a sea domain as well, where we have split them at the design water line. So you can see that the size of the air domain is around 110 meters times 30 times 10 meters high, and the sea domain is almost is the same length and breadth, but we have a bigger depth to it in order to to resolve problems related to the hydrodynamic part. So you can see that after we have our BREP solid hull and our BREP solid domain, we can subtract by a Boolean operation the one from the other, and thus create the fluid domain. So having defined our fluid domain, we can either start defining boundary conditions, or we can, before that, we can start experimenting with the meshing parameters. So since meshing parameters are very important at this moment, we will have a quick look at that. What we have utilized in Midas NFX is the available automesher, and which is very quick and robust, and it is, let's say, advisable that when starting a project to always go through first as a first iteration, give it a try with the automesher and see what are the problems and how you can refine them in the later stage. So first we have used edge size control, defined the sea and the air domain interface in order to refine the mesh and obtain accurate results. We have followed an iterative procedure to determine the suitable mesh size. And of course we have also tried, before getting into the meshing process, to simplify the geometry and check the quality, and lastly check the quality of the mesh. So the final mesh parameters here, you can see that the mesh size, the overall mesh size is 0.124, while the edge size is 0.6, coming to a 1 to 5 ratio, and you can see the refinement in the level between the air and the fluid domain. So now putting this on hold, we have finalized the setup for our fluid problem, and now we go back to see how we start with the modeling approach of the ship structure. So as I mentioned at the beginning of this webinar, what we try to do here is try to propose an integrated workflow, and we have tried to integrate our ship structural modeler, BVB CAFE, together with Midas NFX. So trying to find a workflow that is very convenient for solving, for, let's say, modeling, meshing, and solving ship structural problems. BVB CAFE, short introduction, is a dedicated tool for rapid structural modeling of ships and offshore structures. We have been using the approach for quite a long time now, also for research and commercial projects. We have been creating models in CAFE in order to, because it is intended for ship structural modeling, and it has functions that allow you to very rapidly define the outer hull and also the internal structure, like dedicated beams, parametric stiffened panels, openings, brackets, and all other structural elements related to shipbuilding. When modeling in CAFE, one could, of course, define the structure with a very high precision and very quickly, and also it can start with the initial meshing of the structure. So our proposed workflow is to start with modeling in BVB CAFE, do the initial meshing there, and then export the model directly as a mesh to Midas NFX, which we will see also later on in the demonstration. So the same IGS model that we have used for setting up our hydrodynamic analysis, we directly utilize it also in BVB CAFE. It is the process is refined in such a way that we use the same models in both softwares, so we don't have to go back and forth with changing the different properties of the geometry. We directly use the IGS, we import it in BVB CAFE and create the main structural components of our design, like main transverse, longitudinal bulkheads, double bottoms and decks. And also smaller structural elements such as deck and hull stiffeners, which are modeled as parametric entities within BVB CAFE and can be altered during the design process if needed. So after having an acceptable, let's say, model, we start with the so many times in shipbuilding we start with using a half model in order to assess the situation, and then we could, if needed, we could resolve into a full model. So here you can see that the structural half model that we have in CAFE, we have created in CAFE, we can mesh it. CAFE also utilizes a powerful meshing algorithm for cell elements. And here you can see that the global mesh size for such a structure was 100 millimeters. So, and you can see on the last picture that all properties of materials and thickness of plates and stiffeners are already defined before meshing, and these are data that the project file holds within it, and they are also exported into Midas NFX later on. So we can have a visual check of the assigned thickness, and we can have a similar filter for plotting the profile and material properties. Moving on, we have now created our initial mesh, and we are able to export it directly from CAFE into Midas NFX, and this is done by utilizing the CAFE export in Nastran DAT file and importing it into Midas NFX as a DAT file as well. You can see that this is the whole structure, the mesh structure is how it is imported in Midas NFX, so exactly as it was seen with all properties in BVB CAFE. And what we have chosen to do here is that we have left merging and refinement of the final mesh to do it within the Midas NFX, because also it utilizes some very powerful meshing and mesh repairing functions. So this is, let's say, an approach of very quickly meshing your initial structural design, and without making any precautions on the let's say connections of the meshing. So we leave that behind, and we do it later on when we import our model in Midas NFX. As you can see here, there are some connection refinements between the stiffeners that need to be done, and this is done here within Midas NFX by, of course, there are several functions like merging, repairing, and also refining the mesh if needed. And you can see here some differences between where the mesh had to be fixed and refined. So after we have done a first round of refining our mesh and checking the connectivity of the elements, we have also utilized the tools within Midas NFX to check the element quality and the topology of the mesh. let's say our approach usually is that when we have a model ready to run, we will first run a simple model analysis in order to check for connectivity problems or non-linearity problems, and we would then follow with the linear or non-linear static or any other simulation that we would like to run. You see here also that you can directly then utilize your mesh to mirror it and have a full structure if it is needed in that case. So now again, having set up the structural part of the project, we put that also on hold, and we come back to the fluid part. In this CFD part, we have, as you've seen before, we have set up our domain, we have set up our mesh. We have put the initial conditions like pressure distribution, and we have a transient CFD function to define a wave loading. As you can see, it's a sinus wave loading, and also we have an inlet of 2.42 meters per second, zero pressure outlet, and we have also allowed the hull to translate and rotate around the z-axis in order to get the movement in that perspective. We have a rather coarse mesh because we wanted to get some good idea on the pressure distribution on the aft part, as we mentioned before, and we have used the symmetry, so we only have half a domain in this case, and the results that we are let's say trying to obtain from here is the pressure distribution, total velocity. We get the level set if you want, and also the total deformation of the mesh, because we have also allowed the mesh on the free surface to deform. So we will not go into much details into the CFD analysis, because it really takes a lot of time to go through the settings behind the simulation. However, you could see here how we can utilize directly the analysis and the results of the analysis. So mainly speaking about the pressure mapping of the results. So Midas utilizes a variety of tools for visualizing the results, but also there are specific functions used to map the requested pressure forces on the hull. You could see that with the extract results function, someone could directly go to the different time steps on the of the simulation, select it, and then get the appropriate results. It's like having an Excel table that you can copy and paste into different parts and utilize it as an input. So copying these results, we can then there is a specific function that allows us to use them as a loading to our structural model. And this you can see here. So we have derived the pressure load through the tables shown in the previous slide, and we have mapped them on our structural model and used them to perform linear static analysis. So you can see that as we've seen before, the structural model that we created with BVB CAFE Modeler, we meshed it, imported it into Midas NFX, and now it's ready for use within the Midas NFX platform. We have left all the constraints to be defined in Midas NFX, like boundary conditions and also as you saw, the loading derived from the CFD analysis. And you can see here the results, plotted results from a first analysis as total translation for misses and the overall safety factor. Of course, there are numerous other results that you can derive or insert into your analysis according to what is according to the problem you're solving. So the what is the design verification based on the CFD loads? So what is very important is in mesh generation is to match the structural properties of the hull. The external loads, of course, caused by hydrodynamic pressures on the ship hull. It's very important to be very carefully defined. And also the balance between the external and the internal loads like weight and inertia forces and caused by the hull structure and the cargo. So the selection of appropriate wave loads has to be simulated in that way in order to define the correct loading. So we can then have a look at the collision investigation that we had. So as you've seen until now, we've been only utilizing the two platforms. So BVB CAFE and Midas NFX, we have been sharing the same model basis. So we have two models at the moment. We have the IGS model that we used at the beginning. We have used the same IGS model for both software in order to define these the structural geometry and also the CFD computation. And then we have used also the same FEM model to derive the results for the static analysis. And now you can see that the same models, we can also use it for the collision investigation. So within the same project, we can continue by in that case we use the mirrored the full model in order to have a bit a better inertia force on the hull. And what we are investigating here is the collision between the aft part of the structure and the pillar, which is supposedly part of an offshore structure installation. So ideally, this pillar is fixed in space, and we assign through the Midas NFX tabs for the nonlinear analysis. We have the ability to assign an initial velocity to the tugboat model. And of course, we have to very carefully define a contact between the two parts, between the pillar and the tugboat. So here you can see that we have a nonlinear explicit transient solver that is working. And we have, of course, an array of time steps, and we can get let's say the penetration of the column into the hull of the tugboat. And here you can see some initial results coming from this impact. Which are also, let's say, stored into the same model database, and we now effectively have a full, let's say, analysis cycle starting from the CFD part, going to the structural linear static, and then following with the collision impact analysis at the end, and all within the same platforms, utilizing the same models and getting the results also in one database, being able to plot them for presenting your project. What is also very important is that at any step of this integration, we could go back and change the update our models and rerun our calculations. So we could go back to the BVB CAFE and update our stiffener definitions or plate thickness definitions, which will automatically update our FEM initial model and finally our results at the end. So just to conclude and then have a quick look at the actual software. So we have several pre-processing solver and post-processing functionalities of Midas, which have been showcased here. We have tried to define a workflow which works quite well without any, we didn't have any compatibility issues until now. Of course, we can see that the additional overhead related to fluid structure coupling it's negligible, and even I think with the latest Midas NFX version, with the newest one-way FSI functions, this will be even easier, and we would probably see that in some of the coming webinars. We have of course seen that we need higher computational resources for the CFD simulation. But on the other hand, the FEM analysis, including the explicit analysis, are computationally inexpensive and very quick to solve. And lastly, we have let's say tried to define this integrated approach of FEM CFD-based calculations, which is dedicated to ship and offshore structures. Let's say this is the collaboration between the two software platforms, and considering that the integrating platform is Midas NFX, and you can have your resulting project from there. So thank you for the attention. I hope that I wasn't too quick, and of course I will be happy to answer to any questions. But now I think it's a good time to go to the actual software. So Midas NFX environment, I think that some people must be already familiar with it. So we will start firstly with BVB CAFE. So BVB CAFE is, as I said before, a ship structural modeler. We have the ability to define the hull geometry, the actual the structural elements, as I said before, and several other small structural parameters. So in BVB CAFE we have some innovative approaches related to shipbuilding and design, which is mostly the parametric, let's say, stiffened panels that allow you to have a parametric stiffened panel defined, which can be changed throughout the process of the designing. We have this in the same way. We have parametric brackets, openings, and masses, materials, and plates, and also a very comprehensive database of profiles dedicated to building profiles. What I would like to show you here is that we have defined our structural model in comprises of either strakes or surfaces in that case, and also beams that you can have here. So what I would like to show you is that here we can have groups and model groups, and if we turn them off, you can see that also we have our resulting mesh in the same project file. So this is the initial mesh, which you can see also. I will show you quickly how we can derive it. So here, after having, you can also go through the screening of the properties, like thicknesses or material. You can see material, we have the same material, and you can see thicknesses. So you can see the different thicknesses utilized, ranging from 12 to 15, 18 millimeters blades. And also you can see the profiles. So you can screen the different profiles. So you have T, bulk plate profiles, and they're defined through the database. So all these they're taken into account when we mesh our project. So what we're going to do now is that here we have under tools we have a meshing tab, FEA mesh. We have an element length. So here we define the meshing parameters, like 100 millimeters mesh in that case, and we have also several other parameters that can be controlled from this tab. Going back to our model, we will define a new, we will add a new model group. We will call it mesh new. And now just simply by Control A, we select our whole geometry, and we select the model group where we want to base our new mesh, and we press mesh selected entities. Now you directly see that if we close the other groups and we choose the mesh new, you will see that we have very quickly we have our mesh that we have requested. So lastly, what I wanted to show you is that how we do also we can incorporate changes into that mesh. So if we go back to our model groups, we can very easily add some new beams into the model. If we select one of the beams, this will be default selection, and then we can directly add it by selecting 2 points. We can add sorry, this is I was on the wrong group, but I can do it again. So if we select 2 points again and we add the beam, you can see that the beam is added between the 2 points. We can choose the rotation of the beam. We can flip simply the normal. So now you can see that we have done a change in our model, and we have this additional beam here, but we have our mesh in this other model group. What we can do is that by selecting this model group where our mesh is, we can select the new part, simply mesh it, and if you go back, you will see that the new beam is added into our mesh. So changes can be done, let's say, inherently in this process. So by selecting again, in this case, selecting complete mesh model. Also, I will put here the thickness selection, so you can see that the thicknesses they have gone and properties have gone through the mesh model as well. By selecting the whole model and exporting, we can utilize export, and from this we can select the, as I said before in my presentation, the Nastron DAT file, which would give us a file that we can directly import into Midas NFX. Okay, so this has been done, and we have now we have exported our model, we have imported it into Midas NFX, and now we will go through some simple static analysis just to get an idea. So here we have also, as I mentioned before, we have refined some parts of the mesh. We have connected some nodes, or we have, let's say, merged some parts where needed. You can see that our mesh sets, we have different mesh sets depending on their properties. This is the cell mesh set, this is this type of beams, other type of beams, this T webs, and flanges on this mesh set. So now we have a model ready for starting with your initial conditions. We have defined some generic boundary conditions like constraints around the model just to be able to have a quick analysis. You can see the constraints, they're just simply defined by the static analysis tab, where you have you can define either a constraint, which is you have the selection of between fixed pin, no rotation. We also have an advanced selection where you can choose different symmetric planes or DOFs. And also you have a constraint equation manager where you can have more advanced constraint functions. In that case, we have chosen a fixed constraints around the model, and now we can also define static load. In the same tab, we have the gravity force, we have the force definition, pressure, displacements, and also all sorts of loading and constraints. So let's try to put up some pressure on the top of the deck. We go onto this view. If we want to select only elements on this top, then it's important to select to have a front selection only. Activate it. We choose the pressure, and then we can select objects by dragging our mouse and creating a selection box. You can see that we have selected elements like that. You can use the normal, or you can have a uniformly distributed load by let's say having a plus or minus sign. Let's try here this, and then you can apply. So if we now go, we can see that a uniformly distributed load acting downwards because of the minus sign is distributed on the top deck plate. So now we have everything is set. So we have our model. All properties are there coming from BVB CAFE. We have constraints, and we have also load. What we can do is that we can just define. Here we have defined two analyses. We have defined the linear static and the models that we can see also later. So through linear static, we can just solve that. If you see here, we have the options. We have different options for Midas NFX. You can find different things related to the boundary conditions, their conventions, and also the coloring. Analysis and results. Here you can see this a very important feature of Midas NFX is the being able to scale your simulation into as many cores as you have available. So you can select a number of processors, and you can also enable the GPU acceleration if you have a good, let's say, GPU unit on your PC. So we have defined that, and then we can directly start solving. You will see that the Midas NFX solver is starting, and it's equating the 7 cores that we have defined before. And you will see that it's really quick. Also, the GPU has been enabled, and it's taking into consideration in this computation. And you can see that the total CPU time was 29 seconds, real clock time is 8.9 seconds, so it's extremely quick, I would say. And then directly we have the linear static solutions. By default, we have these three. We have the total translation, we have a shell stress from Mises, and the shell stress safety factor. You can see the displacement. We get this the results bar here. We have the units. We have defined the units in meters, but you can change them at any time. Newton meters, and you can change the convention if you want. And from here you can animate the load pressure. We can also have a look at the von Mises stresses. So you can see here the resulting stresses. You can see that we have a very good connectivity of our model. We don't have any singularities. It's working quite well. It's also very important that the solver does not work with singularities, so the model has to be well prepared. So you can see here the animation also of the stresses. There are several other options in the post-processing. So you can have the contour lines displayed here, and we can also define different slicing planes. So in the Z guide, we can add here. We can add also an X guide, and you see that you can have, yep, so you can slice your model and have specific, let's say, representations of the results. Like here, or if you need to assess some details. Okay, so then coming back, what I wanted to also show you is that, and also not to make this webinar too long, we are now in the post mode. If you want to again go through your model, then you have to go back to the pre mode. So we're back to our model. Something else that I wanted to show you is that how you can also remesh some part of your initial mesh if you want to apply some loads, or if you want to have special consideration of some areas. So directly in Midas NFX we can use the remesh function. You can select by triangle, quad, tri and quad options, and then change the element size. So in that case you can also measure from here. If you have 0.1, we can narrow that down to 0.5, and on quad we can select an area and then apply. Okay, sorry, this was the, let me do that again. So 0.5, yep, okay, yep, okay. So you can see here that according to what we have defined, we have a remeshing part. You can utilize that. You can have you can use your keep boundary node, choose the element size, mesh type, triangle, quad, and tri and quad, and then remesh the appropriate parts. This is something that can be done either in Midas NFX, or a model can come directly, let's say, updated through BVB CAFE and import it again into Midas NFX with the same, having the same boundary conditions as defined and being rerun at the end. So lastly, I will also show you that we can also define the model analysis here. So for defining an analysis, by going to the analysis case, we have all different options like linear, static, non-linear model. backlink, heat transfer, and the CFD also as well. Here we have defined the model analysis, and if we start solving that, so again the solver is launched, its request is the course that we have defined. Mm. Yep, and it's done. So you will see also that this is extremely quick, 21 seconds work clock time, and what we get as a result is we get the different modes. We can also define that the modes or frequencies that we want beforehand, but here we just left it to run. And you can directly get the total translations into different modes. You can see up to the 10th modes, and you still have the animations and different post-processing results. Okay. So just to recap, you have seen the approach coming from the different type of solvers, starting from the CFD, and then to the going to the linear static, and finally the explicit analysis. We have let's say we have tried to show that it's possible to have an integrated solutions utilizing the same IGS model, utilizing the same FEA model between BVB CAFE and Midas NFX, and finally, let's say, concluding into results and being able to access your design through the different steps and reiterate and also change your geometry parameters or thickness parameters, which is very important also in the ship design process sometimes. So I think that I will not want to make this webinar too long for you. I think that this concludes the whole idea, the integration idea, and I will be happy to respond to any questions and also discuss something more specific if it's needed. So thank you very much for your attention, and we'll be happy to talk to you. Yes, so we have this first question, if it is possible to optimize the cell thickness in Midas NFX. This is actually a quite interesting approach. There are options in Midas NFX where there is, let's say, the optimization tabs where you could actually have a set of parameters, which are the let's say in that case the thickness parameters, and run an optimization mode on this, and trying to refine it by selecting the appropriate results in a loop. So this is a very interesting approach, and I think especially for projects in the ship design in this early stage, it's very nice to utilize cell thickness optimization. And hopefully we would have something to show on that topic soon, because it's also very interesting for us. Okay, so if there are any other questions. Okay, so I can see now. So can CAFE support modeling of combined stiffeners, plate and bar? Yes, that's a very basic function of that. Um, so and also the second question, what type of analysis does CAFE support itself? So basically CAFE is a ship structural modeler and preprocessor. It's not a solver on its own, so this is why we are also integrating the two platforms. In one side, the CAFE is let's say offering its very rapid and structural processes, design processes, which are dedicated to the marine industry, and on the other hand, Midas NFX offers the very robust solver and pre and post-processing capabilities, and so the integration is, let's say, that's why the integration is very interesting. So plate and bar, yes, this is also very, as I said, it's a basic function. We have all type of elements, and also depending on the mesh quality that you want, or the mesh size, more correct. You can have beams. You can have beams that are modeled as cell elements and rod elements, or bars, depending on your size. Yes, this also another question regarding if it's possible to prepare vibration analysis, response based on the fluid structure interaction. This is possible, although it is not, let's say, automated. It has to be done by some specific process, and results from the fluid have to be carefully mapped into the structure. This is possible, and it is also, let's say, a matter of preparing well your fluid model, because the structural model is more or less straightforward in that case. Underwater noise analysis, I think it's not an option for the moment, because it requires more a sophisticated, let's say, acoustics CFD specific solver. But FSI, it is possible, and also I think that we will now have a look at a new feature of Midas NFX with one-way FSI in order to utilize it in this workflow and try to update it. Yes, we have experience in noise propagation that comes from sea propellers. Although we haven't used yet the Midas CFD code on this, let's say, type of analysis, but it would be. We think that it is possible, and we would be interested to let's say, to form a workflow for also for this type of problems in the future. Okay, and I see another last question that the last transversal beam is not on, it's not in the post processing here. That was because we didn't in that case we didn't update our model while we were showcasing it, but it was just let's say trying to show how it is done. Updating in the one side, but we forgot to update it also on the other side. But this is, let's say, possible in the to do in the normal workflow. Mm. Um, okay, so some other questions. Is it possible to perform modular dynamic analysis such as random vibration or harmonic analysis by extracting the results from? Yes, this is also possible within the within Midas NFX. It's also, let's say, a separate workflow which is utilizes the same principles. So extracting the loads, extracting the pressures or the loads from the static analysis, and then using them to have dynamic or, let's say, harmonic analysis on the later stage. So this is also possible in this for shipbuilding projects. How the Stephen panels are realized in NFX? So the Stephen panels within BVB CAFE, they are defined as parametric modules that at the end they are meshed. So they are defined as when we export them, we are defined as regular cell elements. And the deck plating is of course always a cell element, but the stiffeners, they can be let's say either beams or they can be also we can have the main member as a cell element and also the flange as a beam, or we can have complete stiffener as a cell element. So the difference is that this depends on the meshing size that you choose. So if you have a very coarse mesh, then you can define the whole stiffened panel from cell elements, and it will be exported into and imported into Midas NFX like that. If you have if you have a fine mesh, this will happen, and if you have a coarse mesh, then you can let's say have a deck plating that is defined by cell elements, and then stiffeners defined as rods and beams. Under the pre-model analysis, so okay, so refining the underdeck area, this is also possible. So of course you can utilize the at any time the remesh function by selecting appropriate let's say elements. In that case, I will just randomly select this area here and 1. So we have triangle, quote, quad. Say apply. So you can see that here we have a quite refined mesh. We have kept the boundary nodes, and I mean, it's of course up to the user to choose what he wants to refine, and what would be the maximum element size or the mesh type in that case. Okay. Yeah, the pre-model analysis. This is let's say what this is in a case. Yeah. So I'm trying to see if there's some other questions. Yes, we haven't. We have used thermal stress analysis, but not for fire simulation. But of course, if someone has the correct boundary conditions coming from a fire simulation, then I think that this would be possible to do. We have mainly used thermal stress analysis for, let's say, heated tanks on ships, or heated heating coils or fluids inside tanks, but not for fire simulation, because it will require, let's say, very good initial conditions regarding the fire. Mm-hmm. Okay, so thank you very much for attending and for all the good questions. Of course, I have to indicate that this is, let's say, a simple demonstration of the integration, and let's say for commercial project, of course, a lot of refinement has to be done, and a lot of additional work to make your project as accurate as possible. And all the tools are there, so it's up to the user to actually conclude on what he wants to use and how he wants to use it. So, okay, thank you very much, and I'll be happy to answer any questions also in person. You can direct them to me or to directly to Midas NFX people. Thank you.